We are today doing the case study, machine tool changing in the Hartford machine, which is in CAD/CAM lab. Next week during tutorial, if I remember to organize it, you will go and have a look at the machine itself. Okay, so you can guess from the video on the other screen that this will be a Geneva mechanism. Okay, so in chapter 7 of the Red Book, you have there is a few sections with so-called special mechanisms. Okay, so I picked one of these special mechanisms to discuss at the lecture. So I think the last one in that chapter 7 is Geneva mechanism. There are a few more. There are, of course, steering and suspension there, which you heard from the, as they say, from the mouth of the horse, right? The guy who does suspension and steering for the motorsport team. And there are straight line mechanisms which we didn't discuss beyond talking about how to generate Kepler curves. Okay, so we have this Geneva mechanism. And this is the picture of the Geneva wheel in the tool changer mechanism. Okay, so it has many different drills and other tools. Okay, so it has to have a wheel or Geneva mechanism with many so-called stations. Okay, so this is the slang in from say in mechanism slang. So the number of these slots, these slots are called stations. Okay, so it has many stations. Okay, and of course it will have the driving wheel, a small one that matches here the position of the driven wheel between stations, and then puts that thing into the slot for the station. Now let us have a quick look again at the thing. So this one has 20 stations. The one in the video has 4 stations, right? So the thing that is driven by the guy is called the driving wheel, and the other one is called a driven wheel or a star wheel. Okay? So if you have a lot of stations like on this one, of course, the driving wheel will be very small and the driven wheel will be very big. If you have only 4 stations, you actually have similar size of the driving and driven wheel. Okay? So, if we talk about the design of this kind of a mechanism, we need to consider a number of dimensions, right? Clearly, diameters of both wheels need to be decided, okay? Distance between the center of these wheels needs to be decided, okay? Dimensions of slots need to be decided, and number of stations needs to be decided. Okay, so these are the, say, design aspects of the Geneva mechanism. And if you are inquisitive enough and find in the library past exam papers for this unit or units that are replaced by this unit, you will see that it happened on more than one occasion that I asked students to design a Geneva mechanism at the exam. Okay? One of the reasons I did it is because it's very easy to mark, because it's not that hard. Okay, so let us look at this picture. Okay, so this is the nomenclature for so this is the simple one, 4 stations, right? So if the pin is not engaged in the slot, we have something which we call a journal bearing, right? So this thing, this surface must match this surface, and these are journal surfaces, and the mechanism behaves as a journal bearing, right? So the driving wheel still can be moving, but the driven wheel is not. Okay, so that's why a Geneva mechanism is an example of a so-called indexing mechanism. An indexing mechanism is the continuous input is converted to intermittent output motion, right? So we can see that for a 4-station Geneva wheel, for each full rotation of the input, the output moves by a quarter of the revolution, right? So what are the applications? Why is it called Geneva wheel? I asked this question, I think, at the second lecture. Who remembers? Who remembers? In watches, this mechanism was used in first mechanical watches produced in Switzerland, and maybe even in Geneva itself, and that's why it's called a Geneva mechanism. And you can see that indexing mechanisms will be used in many repetitive manufacturing operations when you need to advance a workpiece. Or in the case of the machine tool, if you have 20 different tools to be used, then this is one of the ideas of how to change tools in the machine tool. Okay? So, if we look at this one, so this is the situation when the pin is in the slot. So we already noticed that when the pin is not in the slot, the mechanism is essentially a journal bearing. But what if the mechanism is in the slot? Have we seen anything, say the pin is in the slot? Have we seen anything like this before? This looks like a slider crank, indeed. Or even the pin in a slot. I showed a slide with the so-called pin in a slot mechanism, which is essentially a simplified or cheaper version of the slider crank. Now, at this moment, we could perhaps go home and say, okay, we know everything, it's slider crank, we have tables in the book, we have tables in the handout, we have even a Jacobian derived by the lecturer and available on LMS on scanned lecture overheads, right? So this would be possible, but we will not do it because there are certain aspects of the geometry that are so simple that they are better treated using some heuristics for this particular case. Okay. So, if you look at this, we have 3 important dimensions. The radius or the diameter of a driven wheel, driving wheel, and the distance between centers. Now, the question is are we or is a designer able to arbitrarily select these dimensions, or we actually have to consider unavoidable geometric constraints that will tell us what these dimensions must be? okay, for the given number of stations. So what do you think? Is there a connection? Is there a geometrical constraint which we need to consider that will link these 3 dimensions and the number of stations? Or we can just say, oh, I feel that this should be 2, this should be 10, the distance may be 9. Try to observe what happens at an instant when the pin actually enters the slot. The very instant when there is a transition from the journal bearing mode to the slider crank mode. Do we have geometric requirements that specify the position so that the pin enters the slot smoothly? We do. Right? So we have the situation that for the pin entering the slot smoothly, at the instant of the pin entering the slot, we must have the line of the slot, which is this one, perpendicular to the line of the pin, and then pin will go in. If there is no right angle here, we will not have a smooth entry, and this actually will require discontinuous velocity or infinite acceleration. Infinite acceleration would require infinite force, and this would very quickly break our mechanism. Okay, of course, the force wouldn't be infinite, but would be large and would cause deflections of the machine. Okay, but if it enters at the right angle, it is geometrically admissible that it can be done smoothly. Okay, so then now we can do simple calculations based on this picture to give us the relationship between the distance between the wheel centers, the radius of the driving wheel, or at least the radius in the sense the distance from the center to the pin, right? And the radius of the driven wheel measured as from the center of the wheel to the beginning of the slot. Okay? So this is the green triangle we are dealing with. Okay? Angle beta is the angle between slots. Okay? Now, the nomenclature I am using here is directly taken from the slang of people dealing with Geneva mechanism. So they usually call it beta. And beta, of course, is 2 pi divided by the number of stations. Okay? And then we have this simple triangle that has the right angle here, and we can easily see that R2 divided by D is a sine of beta divided by 2, which is sine of pi divided by the number of stations. Okay? And we have R1 divided by D is a cosine of that angle. Okay? So these two equations are linking the 3 design variables. So actually we can choose only one of them. If we choose D, R1 and R2 will get calculated. If we choose R1, the rest can get calculated, and so on. So the number of stations actually defines the geometry. Okay? So I am displaying this again so that it gets recorded. N number of stations, D distance between wheel centers, R1, R2, the radii of the wheels. So having these equations, of course, we can go back to our case study. Okay? And if we look at the number of stations and other dimensions, I'll need to find it in my notes. Okay, so we have the diameter of the driven wheel given, right? So, and beta, of course, is 2 pi divided by 20 because 20 stations, right? So we therefore have very quick calculation for the design, right? So R1 is d cosine pi over n, R2 is d sine p over n, number of stations is 20, so R1 is 177, d is R1 divided by this, okay, which is 179, and R2 is a small one, only 28, as actually predicted by this picture, right? Small driving wheel, big driven wheel. Okay, and if one wants to know the angle beta, 2 pi over n is 18 degrees. Okay? So this is all what we need for the design from the kinematic point of view. Number of stations will be given by our task. Size of mechanism we choose so that it fits our task. And then relative dimensions of D, R1, and R2 are given by these green equations. People would be able to do it, I think, even at the closed book exam. No,